topic, last chapter in the notes. So we'll be looking at fractals today. It's also, after today's session, you can attempt the last assignment, assignment 12. Okay, so this is sort of teaching week 21, and there are 24 teaching weeks in a year. So we've got 3 whole weeks which to do revision. So starting from next week, we'll be doing revision with you. I've also got, hopefully John Borison's going to pop by. He's been working on some work to do with art, mathematically generated art. And I thought, oh, why don't you come by and chat to the graphic students about that? So hopefully he'll pop by next week and demonstrate some of his art. So this is the last section. We're going to look at fractals. Quite a nice sort of, it's not too similar to everything else we've done, but it's sort of drawing pretty pictures. And we're also going to be looking at generating fractal landscapes as well, which is your assignment 12. Okay, so this is from the, I think it's chapter 10 or so in the notes. Okay, so what is a fractal? You may have heard, actually, quick sort of short poll. How many people have heard the word fractal before? Guessing most of you. Yeah, okay. So essentially a fractal is a mathematically generated shape or image. And we say it's mathematically generated. We have a set of rules which govern the generation of that shape or image. It was coined by a guy called Benoit Mandelbrot in the late 70s. Okay, and you may have heard of him, his famous fractal called the Mandelbrot set, which we'll be looking at in a bit. But fractals are interesting because they share a self-similarity property. What this means is, if you zoom in on part of a fractal and sort of blow it up, it resembles the whole of the fractal. Okay, so self-similar means when you zoom in on a section of a shape, it resembles the whole shape. And this property is often seen in nature. Things like clouds, landscapes have this property. So we'll be using fractal landscapes, plants, electricity. You know, it's found in all sorts of places, like seashells, things like that. Okay, and we all look at methods. This lecture is kind of just having a look at a few common fractals, having a look at their properties, and we'll finish off with generation of automatically generated of a frame of a terrain. Okay, ignore that last bullet point. I think that was left over from last year. Sorry about that. Here's a few examples of various fractals in nature. So frost, a snowflake has got a fractal property, the way that the molecules of water crystallize when it freezes, generates fractal. Electricity, so a fork of lightning, if you take one part of that fork of lightning and sort of zoom in on it, it resembles lightning. Broccoli, Romanesco broccoli, and also sort of your normal broccoli that you get down at Sainsbury's. So one floret of broccoli resembles a whole plant. And fern is quite a common example. So here we have 1 leaf of a fern. If you just take one of these sort of stems off, it also resembles the whole fern. So that's what we mean about fractal having self-similarity properties. Okay, so I'm going to talk about some common fractals and their properties. The simplest fractal, and actually it's quite boring, but it's useful for showing what we call fractal dimension in a bit. The idea is called the Cantor set. So this Cantor set, essentially what it is you start with a straight line, and the rule is remove the middle third of your line. So you have a straight line, take away the middle third of it. So, and we keep going on through multiple iterations. So we say at stage 0 or iteration 0, we just have this black line. At iteration 1, we've taken away the middle third of that line. So now we've got 2 lines at iteration 1. At iteration 2, for each of those lines, we take away the middle third. So for every line, you take away the middle third, and you go on and go on and go on. So eventually, what happens is you'll have a shape, which will have, it will be a shape, so it will be something, but it will be made up of multiple lines of 0 length, or very, very close to 0. Okay, so Cantor was interested in things like counting. Okay, have you ever heard of Aleph 0 and Aleph 1? Numbers of numbers. So if Aleph 0, that's how many numbers there are in infinity. Well, Cantor said, well, you can just prove so that's the Cantor set. Very doesn't look particularly pretty, but it's useful to introduce the idea of a fractal dimension. And when we talk about dimension, Euclid, ancient Greek mathematician, he defined as dimension 3. Okay, well, fractals can have dimension which sort of partway between those. And it's also a measure of the complexity of a fractal. So just for a moment, if we let big N be the number of new elements that are added at iteration little n. Okay, so big N is simply the number of new elements. And we're going to say epsilon is the scaling factor of those new elements. So what's the size of those new elements compared to the ones which are already there? Okay, and this, we can relate these two. So if we take the limit as n goes to infinity, so that means what happens when we're at the infinite number of iterations. Okay, so we take the log of the number of new elements which are added at each iteration, divide that by the log of the scaling factor, that will give us our fractal dimension. And we call that D. Now, for a 2D fractal, D would be in the range 1 to 2. Okay, so remember 1 is a line, 2 is a plane. So for a 2D fractal, our dimension will be somewhere in that range. For a 3D fractal, it'll be in the range of 2 to 3. So it won't quite be a solid, but it'll be more than a plane. Okay, somewhere in between. So if we have a look at the example of the Cantor sets, so what we need to do is how many line segments we have and what's the scale. So at iteration 0, we have one line, and I've said, okay, let's say the length of that line segment is 1. Okay, so we start off with a line length of 1. At iteration 1, because we're removing the middle third, we end up with 2 lines. And the length of each of those 2 lines is a third. At iteration 2, we're going to split up 2 lines to give us 4 lines. And it's a third of the length of the previous line, so a third is a 9. And we keep going. So there's a pattern. There's a pattern to the number of lines we have and the lengths of those lines. So iteration 3, we'll end up with 8 lines, each having a length of 127. So if we look at that pattern, follow it on, at the nth iteration, we end up with 2 to the power n lines, and each will have length 3 to the power minus n. Okay. So therefore, we can calculate the fractal dimension of the Cantor set. So using that expression from before, our big N is 2 to the power n. That's how many lines we have. And our epsilon n is 3 to the power minus n, or a third to the power n. Okay, so let's have a look at that limit. Okay, well, using the laws of logarithms, we take the power outside. Okay, so log 2 to the power n we can take the power n outside the log and multiply the log by it. Okay, so that gives me this step. So I've got n on the top and n on the bottom. Okay, so n divided by n cancels out. Okay, so what this means is because the n's cancel out, I no longer have an n in my expression. There's no point having a limit because it's not in terms of n, so I can get rid of the limit as well. So it's just log of 2 divided by log of 3 to the power minus 1, which is a third. Which is the same as saying log of 2 over log of 3, which is 0.63. This means if we were to carry on forever, our Cantor set has a dimension 0.6309. Remember, a point has dimension 0, a line has dimension 1. So it's closer to being a line than it is to being a point. So that's the fractal dimension of the Cantor set. Okay, that wasn't particularly interesting. Okay, it's a useful example to show about fractal dimension. A slightly more interesting one is called the Koch snowflake. Okay, I'm glad I didn't get any stickers there. That's good. And this is interesting because it's a shape with a finite area bounded by an infinite circumference. Right, so, and the rules are, you start with an equilateral triangle. So that's what you start with at stage 0. You place an equilateral triangle, so its base fits along the third of the way along each edge. Okay, so you take an equilateral triangle and place it so it fits a third of the way, or in the middle third of each edge. And then you would just remove the middle line. Okay, so you're adding equilateral triangles to each edge at every iteration. Okay, so for example, if I was to take one line of that my equilateral triangle, so we're just focusing on one edge. At stage n equals 0, we've just got a line. At stage n equals 1, we replace the middle third with 2 lines of equal length. And each of those lines are subsequently replaced by another 2 lines of equal length, and so on and so forth. Okay, so there's stage 0. Okay, that's stage 1, stage 2, stage 3, and I think I've gone at stage 4. And you can keep going, but after a while, the size of those equilateral triangles you're adding are so tiny, you can barely see them. Okay, and this is called the Koch snowflake. And as I mentioned, there's a finite area within this. So within this sort of region here, that's a finite area. But if I was to trace along the outside, the circumference, and I was to extend this to an infinite number of iterations, that circumference would be infinitely long. Okay, so let's have a look at this fractal dimension. Okay, so starting off with an equilateral triangle. So we have 3 sides, and the length of each side I'm going to say is 1, just for reason for calculation. At iteration 1, we no longer have 3, we have 3 times 4 lengths, because each of those 3 lengths now has 4 sides, because we replace the middle third with 2 further lines. And the length of each of those sides is a third. Okay. Stage 2, each of those lines from the previous step is multiplied by 4, and the length of each side is 1/27, so a third, a ninth of a third. Okay, if we carry on, again, at stage 3, we multiply the previous number of sides on the previous iteration by 4, and we multiply 1/27 by 1/9. Okay, so after n iterations, we have 3 times 4 to the power n lines, and each of our line is length 3 to the power minus n. Okay, so that we can use this information to calculate the fractal dimension. Okay, so on the top is a log of how many lines you have. On the bottom, it's log of the length of those lines. Okay, so using the laws of logarithms, okay, so we can split up. On the numerator there, I've done 2 steps. I've taken the n outside, the log, and we can also split up. So the log of a times b is equal to log of a plus log of b, first law of logarithms. Okay, and I can split up that limit into 2. Okay, so on the second one, we have n over n. So those n's are going to cancel out. On this one, as n gets really, really large, this one's just going to go to 0. Okay, a number over a very, very large number is going to be very, very close to 0. Okay, so on the second limit, I can just get rid of the limit because we've got no more n's. And this first limit is just going to go to 0. So I've got log 3 over 4. Log 3 over log 4, sorry. Log 4 over log 3, other way around. So that gives us a fractal dimension of 1.26, something or other. Okay, so remember a line has a fractal dimension of 1, a plane has a dimension of 2. So our outline for our Koch snowflake is closer to a line than a plane, but it's slightly more than a line. Okay, that's the way to think about it. And that's a sort of complexity. Okay, another one. This is quite a neat one. Sierpinski triangle. Okay, and the rules are you start with a filled triangle, normally it's an equilateral triangle. And what you do is you remove an inverted triangle from the middle. Okay, so you take the triangle, you scale it down by half, flip it upside down, and colour it in white. Okay, so if I was to take this triangle, scale it down by half, flip it upside down, and colour it in white, and this is our Sierpinski triangle at n equals 1. And for each of these black triangles, we do the same. We scale them down by half, turn it upside down, and fill it in white. Okay, so this is Sierpinski's triangle. This is sort of a nice sort of mosaic design. It's found in some medieval art. Okay, and if you carry on and carry on, this is what you get. Like with the Koch snowflake, you can only go so far because the triangles get really, really small and you obviously can't see them. Okay, so that's a Sierpinski triangle. Generate these fractals. So in this way, you can use the geometry way, the method of geometry, by taking the triangle, scale it down, and remove it from the middle. There's another way, which is called the chaos game. And this uses probabilities and translations. Okay, so to generate the Sierpinski triangle in another way, starting with a point on the triangle, so you've got 3 vertices of the triangle, so pick any one of those 3 points. Randomly select one of the 3 vertices of the triangle. Doesn't matter which one, perfectly random. Find the point halfway between your current point and that vertex, and then move to that point and mark it. And then you go again. Randomly choose one of the 3 vertices, go halfway towards that vertex, mark the point, and go again. Okay. If you do that thousands of times, what happens is the Sierpinski carpet or Sierpinski triangle appears. And that's called the chaos game. Okay, so what we have is we have this transformation. Okay, so transformation matrix, similar to scaling it by half. Okay, so if xn, yn are your current points, and we choose the bottom left vertex, so we go halfway towards it, we just halve it, and that's our translation. However, what if we chose the top vertex? Okay, well, the coordinates of a new point, or the top vertex, is at xn divided by 2 and yn plus root 3 over 2, and we go halfway towards that. So we can write that in matrix form as this scaling plus that, plus that translation. And final point, if the bottom right one is chosen, again, scale it by half, and we add this point. Okay, so if you were to apply that thousands and thousands of times, okay, that's after 1,000 points. So you have to do it quite a lot of time before you start to appear. So that's 1,000 points, and you can just about make out the Sophinsky triangle. If I keep it going for 10,000 points, okay, now we're getting somewhere. Now you can clearly see that the Sophinsky triangle is appearing. Okay, what about 100,000? There you go. And that looks pretty good. Okay, so there are more than one way to generate these fractals. It doesn't always have to be geometrical rules. This particular one was called the chaos game, and that uses this random number. So you ask the computer to generate a random number. Based on the value of that number, it depends what translation you use. Okay, oh, excuse me. Right, this brings off what I like to refer to as daddy fractals. Okay, this is a Mandelbrot set, and it's the most famous fractal. As you can see here, this is like a sort of screenshot of the opening credits to QI, and this here is the Mandelbrot set. Part of the Mandelbrot set. Okay, and it tends to be the most famous thing. It appears in quite a lot of Big Bang Theory. It appears in and sort of posters and what have you. Okay, so and I'm going to show you now how to draw the Mandelbrot set. And we've got to use complex numbers. So I'm just going to also do a revision of complex numbers for you. Okay, a complex number is made up of two things. It's made up of a real number, which you can express on a real number line, and an imaginary number. Now, of course, imaginary numbers are the square root of -1. Okay, they don't exist in terms of any sort of measurable sense, but they're very, very useful in mathematics. So I is used to denote an imaginary number. So I squared is defined as being -1. So we write complex numbers down. So Z is my complex number. A is my real part, and that's denoted by ReZ, or the real part of Z. B is called the imaginary part, and that's called ImZ, or the imaginary part of Z. Okay, so with complex numbers, we want to be able to add and multiply complex numbers. So if you add two complex numbers, you just add their real parts together, add the imaginary parts together separately. So 2 plus 3i plus 4 minus 2i. Okay, well the real parts are 2 and 4, so we add those two together. The imaginary parts are 3 and minus 2, add them together, just give me 1i. Okay. The product, well, essentially, if we expand out, same two imaginary numbers, or same two complex numbers, sorry, if we expand them out as we would a quadratic, okay, just two brackets, expand them out, okay, and then collect the real parts together and collect the imaginary parts together. Okay, so here we have the expanded out brackets, and we have real parts 8, well, only one real part 8. We have imaginary parts -4 and plus 12, so that gives me 8. But we also have 6 times I squared. Now, I squared is -1. So -6 times -1 is +6. So our product of those two complex numbers is 14 plus 8i. Okay, so we can multiply and we can add complex numbers quite easily. Okay, the Mandelbrot set is actually drawn on what we call the complex plane. And the complex plane is just a way of sort of imagining or picturing where where complex numbers are. So here I have the complex plane. So this horizontal line is my real numbers, the real part of the number Z. The vertical axis is the imaginary part of the number Z. Okay, and so therefore we have two axes, and we can plot a complex number using those two axes. So if we have a plus bi, you go a along the real number line, you go b up the imaginary one, and we plot the point there. And finally, what we need to draw the Mandelbrot set is the idea of a modulus of a complex number. So the modulus of a complex number is simply the distance from the origin of the complex plane to where that number is plotted. Okay, and so if you've got a plus bi, essentially all we do is use Pythagoras. Okay, so the modulus of the complex number a plus bi is simply the square root of the real number part, or the real part squared, plus the imaginary part squared. Okay, right, so bear that in mind. We've got complex numbers, and the modulus is simply the distance from the origin. Okay, so how do we construct the Mandelbrot set? It's actually quite simple. That equation there is all we need to draw the Mandelbrot set. So if we start with some number c, this is your start point. This number c here, it's going to be somewhere in the complex plane. It's going to be some complex number. You start with that number. And we have what we call an iterative scheme. So let's say z starts at 0. Okay. The next value of z is equal to the current value squared plus our starting number c. Okay, so if z starts at 0, z1 will just be c. But z2 would be c squared plus c. z3 will be that c squared plus c, etc. Okay, so this is the what we call the iterative scheme that defines the Mandelbrot set. And what we do is, if the modulus of Zn, so as we keep going, if the modulus of Zn remains bounded, in other words, it doesn't diverge off to infinity, we say that number c is a member of the Mandelbrot set. We call it an escape algorithm. So if your point c has escaped, in other words, the modulus has exceeded a certain value, then we say it's not part of the Mandelbrot set. If it doesn't escape, it's then part of the Mandelbrot set. We normally use 2, okay, as our escape, what we call the escape radius. Okay, so let's have a look at some starting numbers. Okay, let's consider the number 1. So in complex terms, that's 1 plus 0i. Okay, so for the number 1, we have 1 plus 0i. So z0 is 1 plus 0i, because we're starting at 0. z1 is whatever z0 is squared plus 1. Okay, so that's 1 plus 1 can be 2. z2 is whatever z1 was squared plus 1. Okay, so that's 2 squared, 4, plus 1 is 5. Okay, and we can keep going. 26, 677, etc. And it's quite easy to see the modulus, because there's no imaginary part there. The modulus is whatever the value of z is. So after only 2 iterations, our modulus of z exceeded 2. So that's not part of the Mandelbrot set. So at this iteration here, okay, it escaped. What about the number I? So I've got the number 0 plus I in complex terms. Okay, so z0 is 0 plus I. Square that, add I to it. So I squared is minus 1. Add I to it is minus 1 plus I. And the modulus of that is root 2. 1 squared plus 1 squared, square root. So you got minus 1 plus I. If we square that, we get 1 minus 2i minus 1 plus I. Okay, so remember, when we square it, we're multiplying it by itself. Okay, and so we end up at minus I. and the modulus of that is 1. Okay, well, minus I squared, minus 1, plus I, that's minus 1 plus I. And the modulus of that is 2. Now we're actually back. We've been at minus 1 plus I before. We're actually back at a previous one. So this is just going to cycle. Just going to repeat that sort of cyclical behavior. So therefore, this remains bounded. At no point does the modulus of z become greater than 2. So this number, I, is in the Mandelbrot set. Okay, so that's what we do. We repeat that lots and lots of times. So here I have the plot of the Mandelbrot set. Across the horizontal axis, my real number part goes from minus 2 to 1. And the imaginary number part goes from minus 2, oh sorry, just below minus 1 to just above plus 1. So for each point in this domain, we go through that iterative process. If the modulus of that number z for each point, if it ever becomes greater than 2, it's not part of the Mandelbrot set. But if it remains bounded, we draw the point in black. And this gives us this nice pretty shape, which is known as the Mandelbrot set. Okay, so I'm just going to just have a look at convergence behavior. So let's take a different starting point. Minus a half plus a half I. Oh, excuse me. If you calculate the various iterations for that, okay, I'm just going to show you where you end up. Okay, so on the first iteration, you go down there. Next iteration, we're up there. Okay, so all of these points are the various values of z plotted on the complex plane. Okay, go over there, up there, and you can see it sort of never escapes. Those points are never more than 2 away from the origin. Okay, and I can keep going that pretty much almost forever, and it would always stay within inside. Okay, it sort of makes a star shape. What I'm going to do now is move my point slightly to the left, and I'm going to start at a point outside the Mandelbrot set there. Okay, so that's my first iteration. There's my second. Okay, we're within the sort of modulus of 2 at the moment. Modulus of that number is less than 2 at the moment. The third one, okay, we're doing all right so far. Oh, hang on. Starting to get a bit further away, and it eventually starts to diverge. Yeah, there we go. Yeah, it's miles away now. The next one just goes off. Okay, so that's the convergence behavior. So if the point is labeled as coloured in black, it means it always stays within 2 of the origin. If it's white, it means it's escaped. Now that's all right, very well. A bit boring being black and white though. So we can improve it. We can colour in the points depending on what iteration they escaped. So those points which aren't a member of the Mandelbrot set, some of them would have escaped sooner than others. Okay, so what we can do is we can colour in the points depending on when they escaped. So we use a matrix M to keep track of the iteration number when each point escaped. And we can also normalise this iteration count so the colours look smooth. Okay, you know, this is not something that I ever ask you to apply, but we can normalise this iteration count. Okay, so there's the same Mandelbrot set that the points are coloured depending on when they escaped. So the blue ones escape pretty much straight away. Okay, as you get sort of the greens and yellows and reds, they took longer to escape the Mandelbrot set. Okay, so then it makes nice pretty pictures. That's so for example, every point in this blue region escaped from the same iteration. But we can normalise these iteration counts and it just smooths out the colours. And it gets all a bit psychedelic now. sort of a bit hippie, tie-dye sort of stuff. Okay, so that's a Mandelbrot set. And I mentioned fractals have self-similarity property. We can zoom in on parts of this Mandelbrot set and blow it up, and we can see little mini Mandelbrot sets in it. Okay. So what I've done here is, I think I've taken, can you see there's a little spike thing there? Around about there. If I zoom in on that. Okay. And this is just zoomed in, and you might be able to, I don't know whether you can make it out, but we've got this point here. That's a mini Mandelbrot set. It looks like the main Mandelbrot set. Okay, we could sort of have a look around. It's all sort of spiky and sort of, yeah, like I said, a bit psychedelic. Okay, oh, there's if you zoom in a bit, there's one. I found one. So we can zoom in on this one and find mini Mandelbrot sets within that one. Okay, so this is sort of the bit between the main bulb and the sort of other bulb. There's sort of two sort of circles, they're called bulbs. And in the bit in between is known as the Valley of the Seahorses. It sort of looks like a seahorse tail. Okay, all of these are generated using MATLAB, and the code, I think I've given you the code in the notes. And there's a nice sort of swirly patterny thing. Okay, now this one, that zoomed in like sort of 1 trillion times. It sort of really zoomed in. I mean, for example, if you look at the all of the values on the axes here, notice they don't change because it's sort of zoomed in so many times. Look, there's another little Mandelbrot set in there, and you can zoom in on that set and find all the other ones. So it's self-similar. Quite a nice sort of quite a nice shape. Okay, so that's a Mandelbrot set. Also, I mentioned at the beginning, we've got ferns have a fractal nature. Okay, an English mathematician called Michael Barnsley found a way of generating ferns using the chaos game. So basically what you have is you're given a start point, so you've got coordinates of a start point, x and y, and you generate a random number, somewhere between 0 and 1, and depending on what number you have, you apply one of these 4 translations. So if your random number is less than 0.01, you apply that translation. If it's between 0.1 and 0.86, you apply the second one, and so on and so forth. So there's a 1% chance you do the first one. There's an 85% chance you do the second one. Something like 7% chance, 3 and 4. Okay, so if you keep playing that game, same way as we did with Sierpinski. Okay, so you have to do quite a few points. Here we have, this is 1,000 points. So I've used green for each point. You can't really see anything yet. Okay, so that's 1,000 points. This is 10,000, 100,000, and finally 1 million. So you see it sort of resembles a fern, and that's known as Barnsley fern. Okay, and it's a sort of fractal in shape. It's quite a nice application and translation makes of these, to be honest. Okay, so this brings me on to what is essentially going to be your assignment 12. This is fractal landscapes. Now, natural landscapes also share the self-similarity property. So, for example, if you take a mountain, take the general shape of a mountain, if you zoom in on various sort of peaks in that mountain and then sort of blow it up, it resembles a big mountain. It resembles the whole thing. You can zoom in on rocks, blow it up, it looks like a mountain. Zoom in on like little pebbles or little stones, they resemble mountains. So we have this self-similarity property. What we could do is we can automatically generate realistic-looking landscapes. Now this is incredibly useful. So especially in the computer games industry, and quite a lot of games now are what we call open world, where you have massive sort of domains or massive areas for which the game exists in. The developers of the game aren't going to have to want to define each sort of point. So what they do is they write software to automatically generate the terrains. And this is an example of fractal landscapes. Okay. So, and the method used, one of the methods used is called midpoint displacement algorithm. It's quite simple. Okay, you start with a line, or you start with just 2 points. So 2 points on a line, and you calculate the position of the midpoint, which is just the average of the coordinates of the 2 endpoints. So add them up, halve them. So that's the y coordinate there. Then what you do is you displace, or move up or down, that vertical coordinate, the y coordinate, by a random amount. So r is going to be a random amount, and this random amount is somewhere in the range, what I call r min to r max. Okay, and that's r min, r max is what you sort of define you want it to be. So all you're doing is you add something to your y coordinate at the midpoint. So you're displacing the midpoint, hence the name of the algorithm. And furthermore, at each iteration, you reduce that range. So for example, you might want to say, if r min and r max starts at -1 and +1, you might want to halve the range each time. Okay, so it reduces the value of our displacement. And you just keep repeating that over and over again, and eventually you get a nice fractal landscape. Okay, so here we have a line. Okay, that's my stage 0. What we do is we take the midpoint and we move it up or down. So I'm going to move it up, just so it makes a mountain. And it moves up by a particular amount. That amount's going to be r. Okay, then we've got 2 lines. So we've got this line here and this line here. So each of those 2 lines, we calculate the midpoint. So it's going to be about there and there. And we move the midpoint up or down a bit. Then we've got 4 lines. So we take each of those 4 midpoints, move them up or down a bit. Okay, and we keep going. I've stopped after 3 iterations, but if we keep going, we get a nice sort of fractal landscape. Okay, so what I want you to do now is, I've been talking for long enough. Got another one of my activities. Okay, have you got any money? You need a coin. Okay. By the way, I'm not asking you for money. You looked at me strange when I said that. If you get a coin out, because you need something to random. You guys talk about any spares? Okay, has everyone got a coin? Or something to, something to randomly decide between 2 states? In other words, so a coin's useful. Okay, what I want you to do is generate your own fractal mountain. Okay, so, all right, guys. I've sort of engineered it slightly because it's not quite as random. I want to engineer it slightly. So, what we have is we've got a point which starts at 0, 0 and ends at 32, 0. Now, I've deliberately chosen 32. Well, why have I deliberately chosen 32? Why 32? Exactly. 32 is 2 to the power 5, so it's nice and easy divided by 2. Okay, so start in iteration 1 with a vertical displacement of 24. Again, I've deliberately chosen 24, so it's nice and divisible a number of times. Okay, so what I mean by that is find a midpoint, so halfway between, and then vertically displaced by 24, and mark that point. Right. So everyone should have the same first point marked. For all other, so that's your first iteration. For your second iteration, what I want you to do, oh sorry, for n equals 1, what I want you to do is flip a coin. If it comes up heads, we're going to add a number, and if it comes up tails, we're going to subtract it. So my next midpoint would be x equals 8, which is about there. I've got a head. Okay, that means I'm going to add my r to that point. I mean, you flip a coin, you might get different, so don't just copy what I'm doing. Okay, and if in this case t is 1, so I'm going to add 6t, 6 times 1 onto 12, so I'll get 18. So I'm going to mark that point there. Okay, so that's the halfway point along this line. Find the halfway point. I tossed the coin, came up heads, so I've added 6. For the other point, I've got tails. Okay, so the midpoint between these two is around about 24, is about there, and I'm going to subtract 6, and I'm going to mark that point. Okay, so now I've got 4 sort of lines. Imagine there's a line there, so one line up there to there, down there, and there. So I've got 4 midpoints now. So the first midpoint would be 18 plus 0 will be 9, so it will be about that point there. So I'm going to toss a coin. Tails. So that point there is going to get reduced by that amount. So half of 6 is 3. So 9 minus 3 gives me 6. So it's there. Okay, halfway between these 2 points is about there. So I just put, okay, I'm going to toss a coin. I've got a head. So that's going to go up. So I'm going to go up by 3. So that's going to give me that point. And we keep going. Okay, so toss a coin. Oop. I've got tails. So my halfway point is about there. So I'm going to subtract 3. So I'm going to get it to be there. Okay, toss another coin. There's a tails again. So halfway between here is there. Minus 3 goes down to there. So now I've got 1, 2, 3, 4, 5, 6, 7, 8 to do. And I go again. This time, instead of 3, I'm going to do 1.5. I'm going to add or subtract 1.5, depending on the outcome of the coin. So that's tails. So that point gets subtracted by 3. Heads. That's a bit of a lame. Oh no, sorry, just subtracted by 1.5, not 3. So that's halfway point is around about there. So add 1.5 is there. Tails, so subtract 1.5 from that point. Tails, so I'm going to subtract 1.5 from this point. Okay, so I'm finding the halfway point, which is about there. Tails, so subtract 1.5. That's another tails. So where are we? Halfway point between these two, subtract 1.5. Heads, so it's about there. And heads again, so I add 1.5. Okay, so if you do the same, find for each pair of points, find the halfway point, flip a coin. If it's heads, you go up. By this time, if we were to go again, it would be 0.75, or down, 0.75. Okay. And then what you do is just draw a line between each pair of points. That's what mine looks like. So that was after how many iterations? So we had 1, 2, 3. That was after 4. Okay, so if we all do 4 iterations, we're going to have 16 different. No, it's going to be about. No, it'll be more than 16, wouldn't it? We're going to have lots of combinations of different landscapes. So yours may not look like mine. Mine looks a bit naff, to be honest, but it's random, so we can't really tell what it's going to look like in the end. Okay, so that's this general method. Halve it, find the midpoint, so find the halfway point, randomly decide whether you're going to go up or down, and go up or down a bit, and then for the next iteration you halve that amount that you add. Okay.
Anyway.
And you can embellish your landscape or your mountain however you want. Okay, so do you get the general idea for the midpoint displacement? So that's your assignment 12. Although there is a slight complication to it. Haven't made it that easy. Okay, well, as we saw with my example, we came out with a pretty rubbish landscape. Okay, so we might want to have some way in which we can sort of influence the look of the landscape. It's still going to be random. We want some way to influence it. And this is where we introduce the roughness parameter. Okay, so the amount of which we perturb or we move our midpoint up and down at each iteration is sampled from a distribution somewhere between R min and R max. And we reduce the range of that distribution. Okay, so for example, if we started with -1 and 1, and we were to reduce it by half each time, on our second iteration we'd have -1/2 plus 1/2. On third iteration we'd have -1/4 plus 1/4, -1/8 plus 1/8, etc. Okay, so that's halving each time. But we don't have to halve each time. We could do. We can introduce a roughness parameter. And what we do is we say that the range is equal to 2 to the power -2 times n times h. This is just one way to do it. N is your iteration number. H is your roughness parameter. That's usually between 0 and 1. If you want a really smooth landscape, you set H to be closer to 1. If you want a rough landscape, you set H being closer to 0. So for example, if H is 1/2, -2nh would just be -n. And so you're halving the range each time. If H is 0, then we've got 2 to the power 0, which is 1. So we're not changing the range at all. If we started off with -1 plus 1, we'd end up, the range would be that each time, and we'd end up with just random noise. When H is equal to 1, we've got 2 to the power -2 times n. Okay, which is like 1/4 of the range each time, which results in a very smooth landscape. So by that I mean, there you are. Here's a few random ones. The same, I've gone up and down in the same points. But when H is 0.2, you've got quite a rough one. When H is 1/2, you get somewhere in between. When H is 0.8, you get a smooth landscape. Don't know why there's a gap there. No, there's not a gap on the actual plot. Okay, so H is like if you want a landscape to be nice and smooth, okay, you use a bigger value of H. If you want it to be all rough and jagged, use smaller value. Okay, so with that in mind, flip over your activity sheet and do the same thing, but using different values of H. So when H is going to be 0.8, we're going to have 6t times 2 to the power minus 0.8 times n. Right, so starting at the same points again, toss a coin to decide whether you go up or down. And this time we're going to perturb by a different amount. So the first one's going to be up or down by 6. So my first point is going to be there. And second point is also down by 6. Okay. Okay, now I'm going to go up. So here is my midpoint. 2 to the power 0.8. Oh. Okay, so we're on the second iteration. So we got put 2 to the power minus 0.6. It's 0.329 and times that by 6. So we're going to go up and down by 1.9. And then you're going to multiply that again. Sorry about that. Okay, so we're going to. So in this case, I had a head, so I'm going to go up by 1.9. Find the midpoint. Toss a coin. That's tails, so I'm going to go down by 1.9. Toss a coin. Heads. So midpoint is about there, so I'm going to go up by 1.9. And tails, so midpoint's about there, so I'm going to go down by 1.9. Okay. Believe it or not, that was meant to be a fairly smooth one. In other words, it's not going up or down jagged. I think we'll leave this activity because it's quite a tricky thing to actually do quickly. Ooh. Okay, so that's a roughness parameter. So the value of H depends on how rough you want your landscape. Okay. I thought I'd show you some MATLAB code because this will help you with assignment 12. Now, assignment 12 is writing a MATLAB program to generate a landscape, but it's generating it in 2D, which we'll talk about in a minute. Okay, so there are a few things which, actually, I might as well show you the actual code. There are a few things which will help you out here. We'll show you the answer. Okay, for some reason, my computer's running at absolute snail's pace. Oh, there we go. Don't know if something's running in the background, but it's not quick. Okay, right. So this is my code for drawing a 1D fractal mountain. Okay, so what I've got here is at the top of the code, Okay, I have my roughness parameter as a half. My n max, that's the number of iterations I'm going to go to. Don't have n max being 10 or 20 because it will take forever. Okay, because the amount of work you have to do at each iteration follows an exponential function. So n max is my maximum number of iterations. So everything's nice and easy, whole numbers, I've chosen the length to be 2 to the power n max plus 1. Okay, so that means I'm pretty much only dealing with whole numbers across the x direction. Step, what that means is how far you have to step from one point to the next. So at the start of it, the step is 2 to the power n max. So that's like 0 to 32. One step would have been 32. So a half step is simply step divided by 2. So when I say step, that is the distance between two, horizontal distance between 2 points, and a half step is halfway between the 2. Okay, so I'm going to start with initializing some arrays. Now x is just going to be 0 to length. Okay, so if I was doing the this example, it'll be 0 to 32. Y starts off being all zeros, because Y will give me my perturbation up or down. Okay, so if we go through the iterations, for n equals 1 to n max, so we're going to stop at n max, calculate the range, 2 to the power minus n, or 2 to the power minus 2 times n times h. So that gives me my range. Then what we do is we loop through all the midpoints. Okay, so the first midpoint will be 1 in step lengths of step. Okay, so whatever step is at the start, step will be 32. So 1, boom, add 32, you end up at 33. Okay, and we stop at length minus step. Okay, so if I just use the activity as an example, okay, so that's my first x coordinate, that's my last x coordinate, and to start with, my step is 32. Okay, so we've only got 2 points. Half step will be 16. Okay, so that will give me my x coordinate. Okay, and then I calculate the y value. So yi plus a half step. Okay, so that's the middle point. 0.5 times yi plus step. So those, let's say I is 1, I plus step will be 33. So that's my start point and my end point. Average them, add them together, divide by 2, or add them together and times by half. Then I'm adding 2 minus 2 times rand. Sorry, 1 minus 2 times rand. Why am I doing that? Well, if I just... Rand gives me a random number between 0 and 1. Now, sometimes I want to go up, but sometimes I want to go down. So I want a random number between -1 and +1. So what I can do is say, well, 2 times rand will be a random number between 0 and 2. 1 minus that random number will be in the range -1 to +1. Okay. As you can see, sometimes it's negative, sometimes it's positive. So that's in the range -1 +1. So 1 minus 2 times rand, oops, just gives me that sort of, it's the coin toss in other words. Okay, times range. Okay, so that's going to be a number between -1 and +1, times it by the range will give me a random number in that range. Okay, so that's, on the first iteration, that's only going to be 1. You're only going to move 1 up or down. Half the step, half the half step. And then I've got a little plot thing so we can see it as it's going along. Second iteration, reduce the range. Okay, and this time calculate the midpoint. Now, because step and half step have reduced by a factor of a half, okay, you're going to have more points. Okay, so let's see what happens when I run this. As I mentioned, it's going very slow for some reason, this computer. Okay, there we go. So each halfway point, it generates the height, and then it plots it. Every time I run it, it'll be a different. It will look different because it's all random. Okay. So that's your midpoint displacement. Why is it running so slow? I don't get this. Have I asked it to run? Oh, maybe not. So if I run it a third time, so that's a random landscape. It doesn't look that impressive. It's only 1D, or between 1 and 2D, somewhere between the two. Okay, in your assignment, I want you to create a 3D landscape or a 2D fractal. And I want you to use the 2D midpoint displacement algorithm. We've just seen this. That's just on the slide. Come on. Here we go. Okay, so imagine that, but now we're going to go for 2D. The concept is exactly the same. Calculate midpoints. Calculate the random number R, move your midpoints up and down. Okay, so imagine you start off with this this is your landscape. Imagine you've started off with a flat square. Okay, so this is looking down from the fan view on your landscape. For each corner, okay, you find the halfway point. So here you can see the grey point is a halfway point along each corner. And so to find the height at that point, you take the height of the two adjacent points, add them together and halve it. And for each of these grey points, you move it up or down. And then, using the new grey point, you calculate the midpoint there. So that white point is a quarter of the sum of those grey points. Okay, so calculate where that midpoint is, move it up or down. So then you've got 4. So now we've got 4 squares. So we do the same thing again. I calculate a point about there, move it up or down. There'll be another point there, another point there, and a final point there. So for each of those 4 squares, you do the same thing again. And you get, if you do that, okay, so starting with a flat square, okay, that's the first one. It doesn't look very good at the moment, so that's okay. We've got halfway along each edge. We've also got a midpoint in the middle. Okay, so there we've got 4 squares. Now for each of those 4 squares, we do the same thing again. Remember, it's all random, moved up and down in a random amount. So now we've got 4 by 4. We've got 16 squares. For each of those, split them up, calculate the midpoints, move them up or down. And we keep going. And eventually, you get your landscape. Okay, so I'm just going to show you the generation of that. I'm not going to show you the code because that's your assignment. Oh my word. Let's move that down there so you can't see. Why isn't it? Oh. I'm trying to select it, it's not. Oh my word, just check on it. What's going on here? Sorry? Why are you on mute? Chrome. Right, Chrome's going.